All right, welcome. Today, we are popping the hood on one of the coolest fields in tech right now, physical AI. We're going to break down the actual blueprint for building a humanoid robot, everything from its metal skeleton to its thinking, learning mind. So, where do we even start?
This question used to be pure science fiction, right? But now it's being answered in the most advanced labs on the planet. Building a robot that can think and move isn't just about writing clever code. It's about closing that huge gap between digital smarts and the physical world. And the first step? Well, it might not be what you think.
Before we even get to the nuts and bolts, we have to understand the core idea, the foundation that makes all of this possible in the first place.
So, what it really comes down to is this. Physical AI isn't just an algorithm sitting on a server somewhere in the cloud. It's an intelligence that can actually do things. Pick up a box, walk up a flight of stairs, or figure out how to get around a messy room. It is literally the bridge that connects a software brain to a body that can take action.
Okay, so we've got the foundational concept down. Now, it's time to actually start building this thing, at least in theory. And the first huge challenge is just engineering a body that can move with precision and, a purpose. Now, this looks super complicated, but you can really break it down into three main parts. First up, you have kinematics, which is basically designing the skeleton. Then you've got dynamics, which is all about understanding the physics of how that skeleton is going to move. And finally, actuation, which is giving it the muscles to make it all go.
So let's start with kinematics. This is all about the pure geometry of movement. It's where engineers answer the big questions like, how long do the legs need to be? Or how many joints does an arm need to actually reach out and grab something? This is the robot's architectural blueprint, long before we even think about real-world forces.
Okay, so you've got the skeleton designed, but a blueprint can't walk, right? You have to apply the laws of physics. And that's where dynamics comes in. Seriously, the math here gets incredibly complex. It's not just about moving an arm. It's about calculating the exact force needed to keep a robot balanced on one foot if you push it, or how it can absorb the shock of a jump without falling apart. This is what turns a static 3D model into something that can actually handle the real world.
And that brings us to the final piece of the physical puzzle, actuation. Think of the control system as the robot's nervous system, sending out signals. The actuators, these are the motors, the hydraulics, all the things that create movement. They're the muscles. This is the moment a digital command like step forward becomes an actual physical step. So, our robot has a body. It can move. Great. But how does it know where to go or what to do? Right now, it's just a puppet. It's time to build its mind.
The first part of any mind is perception. It has to be able to sense the world around it. And honestly, the best way to understand this is to just compare it to us. Where we have eyes, the robot has cameras. Where we have ears, it's got microphones. And for touch, it has a whole array of different sensors. This is how it takes in the world.
All that data, all the images, the sounds, the pressure readings, it all gets piped into the AI model. This is the central processor, the robot's brain. It's where the system takes everything it's perceiving and decides, okay, based on all this, what do I do next? This is the thinking part of our thinking, moving robot.
And here's what's so crucial. This mind isn't static. It's not just running a simple, pre-written program. Through adaptation, through machine learning, the robot gets better over time. It can learn that, hey, this floor is slippery, so I should change how I walk. Or it can figure out a better, more efficient way to pick up a box. This is what makes it truly intelligent.
So we've walked through the whole blueprint in theory, but this isn't just theory anymore. Let's take a look at how this is all taking shape out in the real world, with real companies building amazing things.
I'm sure you've seen videos of some of these online. They're pretty mind-blowing. You've got Atlas from Boston Dynamics, which is famous for its insane acrobatics. It's all about pushing the limits of what's physically possible. Then you have robots like Digit and Tesla's Optimus, which are being built for more practical jobs, like working in warehouses or on assembly lines. Each one shows a slightly different vision for the future of this tech.
And the potential uses here are just huge. We're talking about everything from making our factories more efficient, to assisting the elderly, to sending robots into disaster zones that are too dangerous for humans. This is why this stuff matters so much. The potential impact on our world is enormous.
But with that kind of massive potential comes some really big questions and a whole lot of responsibility. Building these machines is no longer just an engineering problem. It brings up some of the deepest questions we have to face as a society.
We have to talk about the tough stuff. I mean, what happens to jobs? Who's responsible when a fully autonomous robot makes a mistake and someone gets hurt? These aren't just far-off sci-fi problems anymore. These are very real conversations happening right now that are shaping how this technology gets built.
And this quote really just gets to the heart of it all. Yeah, the technical challenges are huge, but the ethical and societal challenges are just as big, if not bigger. The end goal has to be progress that benefits everyone, and that means we have to be thoughtful and very careful about how we design this future.
So what's next? Well, things are moving at an incredible speed. The big focus areas right now are things like creating way better batteries, giving robots a more human-like sense of touch, and of course, making the AI brains inside them even smarter and more adaptable, so they can learn on the fly.
And all of that leaves us with one final, and maybe the most crucial question. As we're designing the code for them, as we're writing the rules that will guide these machines, it forces us to look in the mirror and ask, what rules should we be designing for ourselves? Because in the end, the most important blueprint we're creating might not be for the robot, but for the kind of society we choose to build alongside it.